Good afternoon, everyone. Again, these are lectures 35 in high-dimensional probability and applications in data science. Last class, we started developing mathematical foundations of machine learning, specifically of supervised learning. We're aiming at a framework that's sufficiently general to encompass linear regression and nonlinear regression and binary classification and neural networks and so on and so forth. Very, very general and flexible mathematical framework. Let me repeat one more time the setup, the framework in which we'll be working. And if anything is not clear, ask me now when we do this, because later we'll not repeat it anymore. Okay. So one more time. Supervised learning. The main object that we're working with is a pair of random variables or vectors. XY. It is not independent. And in fact, it is good that it is not independent because we think of Y as being the dependent variable. The goal is to predict Y from X. We don't get to see the distribution. We do not know the joint distribution of X and Y. All we can see is the training data. Training data is simply n independent and identically distributed pairs of these random variables distributed as xy. So they're coming from the same joint distribution as xy, and we get to see n pairs. We think of Y as a label. For example, cancer, no cancer, and X would be the predictor random variable, such as the symptoms. This is the information that we have available, and we would like to predict, let's say, yn+1 from xn+1. If the new patient comes, then we would like to have the correct diagnosis. That's called the oracle. We would like to build the oracle H that takes X to Y. As we discussed last time, if we don't restrict this problem any further, then the oracle that we can build would be just a function that takes x1 to y1, x2 to y2, x3 to y3, and xn to yn, and nothing else. And the oracle, for example, it could just assign value 0 to everything else. It's a very stupid oracle. All it does is just memorizes the training data. It just knows where the training data goes. What's the labels of the training data? It's like that circus dog that just memorizes the example that's given, but doesn't understand how to count or how to add numbers. This problem is called overfitting. To avoid overfitting, we will look for the oracle H from a predefined set of oracles, predefined set of functions, and we will find the best one. That's how we restrict the set of possible oracles. So we choose, it's up to us, we choose the possible allowed set of oracles. So we choose what's called a hypothesis class H. Those are the candidates for oracle, for the oracle. How do we find the best possible candidate? For any candidate, for any oracle from the hypothesis class, we would like to estimate, we would like to minimize the risk. And we compute the risk by looking at how the oracle fits the distribution. So we look at h of x, and we would like to compare it with y. Ideally, h of x equals y, it's a perfect oracle. But if it's not, we measure the discrepancy with some function, let's call it loss function. So we choose also a loss function, which for practical purposes could be the quadratic loss. And the quadratic loss is just the square of the difference. So r of h would be, for quadratic loss, would be h of x minus y squared. If y is a random, if y is real value. Okay, so if you're at some point get a little confused and tired of all this abstract notation, just go back to something specific, which is quadratic loss. So we evaluate this risk for each h from the class, and ideally we would like to choose the best one, h star, the one that minimizes the risk over all possible candidates, from the hypothesis class. The problem with this is that we can't evaluate the risk because we can't take expectations. We can take expectations because we don't get to see, we don't know the distribution. We only see this data. So we can't take full expectation. So instead of taking expectation over the entire distribution, we take expectation over the sample. And that becomes the empirical risk. So let me mark this as not computable. And what is computable is the empirical risk. So how do we do that? Instead of taking expected value, I just take the average over the sample. Okay. This is computable, and we can take the best possible oracle, the one that minimizes the empirical risk. That becomes computable. Because the empirical risk is computed from data, we call this a training risk, the training error. That's what, to compute it, we train our data, to train our algorithm. So this is training error, just another name for it. And the actual risk is called the test error. It's called the test error because xn plus 1 and yn plus 1, the new patient that comes, has the same distribution as xy. And so if I put here n plus 1, let me do this. Imagine I have n plus 1 here and n plus 1. The value doesn't change because it's the same distribution. And so this is a test error for the new patient. That's what we would like to minimize. And we minimize this by minimizing the empirical risk. This we can do, and the algorithm that does this is, well, we hide that a little bit. We don't say what is the computational cost of doing this, of minimizing over in potentially infinite hypothesis class. So that's where the theory is a little weak. Not weak, but it doesn't specify that. But if we can do this, for example, by optimization, the resulting algorithm is called the empirical risk minimization algorithm. We already described it, but this is the algorithm actually, but let me just repeat it, that it takes two steps. One is a training stage, where for input data, we input the data, we compute the empirical risk, minimize it over the hypothesis class, and we compute H instance. So this is our winner. This is the oracle that we output. And then if a new patient comes, we can make prediction on query X. So for example, a patient comes and say, I have these symptoms X. We just put this in our oracle and output what the oracle says about X, H and star of X. That's ERM algorithm. Any questions? Good. That's a classical framework of machine learning, of supervised machine learning. Cool. And now the results. Okay, how do we know that we can actually, that the result will be good? How do we know that the result will not, that we will not doing overfitting? That's where we would like to have generalization, good generalization power of an algorithm. Generalization refers to the ability to not overfit, to not only memorize the training data, but also to generalize it to new patients, to new unseen yet data. And here is a generalization error, generalization bound. We proved it last time. What we would like to know is, for our oracle, this is the oracle that we compute, what is the risk? In other words, what is the error that this algorithm will make on the new data, on the unseen data? If the algorithm just memorizes the data, the error will be big. If the algorithm kind of understands the data, the error will be small. So that's why we want to compute that. The best we can ever do is the actual minimization of the true risk over the entire population. That's where we kind of play God. We say, if we knew everything, completely everything about the symptoms and the diagnosis and how human body works and everything, then we would know this expectation, we would minimize it, and that will be our perfect oracle with the infinite amount of data and with the infinite power of prediction. So this is the best we can ever achieve. Plus, and that is an interesting term that is actually called the generalization error. This is a cost of going from infinite power and infinite population to just our data and just our power. And we proved that it is bounded by the discrepancy, the worst discrepancy between true and empirical risk on the class. Ignore constant 2, it's not important. It's a little lemma, it's just, it took us 3 steps to prove, basically, but I'll not repeat the proof. But that is what we'll work with now. This lemma will be our main focus. We would like to bound this term better. It formally just gives us some answer, and it's computable. But what does it say really? How do we have an algorithm, let's say. I'll give you an algorithm. What is this? Can you bound this? Can you know how many samples you need for this to be small, less than 100, less than, for example, 0.01? Can you do that? So let's work with this bound a little bit. We'll be working with this supremum. Okay, that's where the new material will start. Ask me questions. If anything is not clear now, this is the time. This is a good time to ask, or maybe make suggestions. I guess you're good. Everything is clear? Yeah, perfect. Okay, excellent. Okay, let's demystify this term. This is not a very good thing to have. Supremum over this thing. Whoa, what is this? Okay, let's do it. Let's move it here. is supremum over H. Let's just remember what Rn of H was right there. And what R was right there. It's just the empirical risk versus the true risk. It's the supremum of the sum of 1 over n. Empirical risk is this. I'm just rewriting. Loss function of h of x I, y, I. Perfect. Minus expected value of the true risk. Nothing happens here. Just rewrote what it is. Now let's make this one little trick. Because x and y has the same distribution for any point, x, y, the same distribution as x, I, y, I. The data comes from the same distribution. I just artificially put i's here, like that, because of the same distribution. Agreed? And then I put it inside the term. So it's the sum of these terms, just like that. And because of 1 over n, there is fraction 1 over n in front of the sum, so if I can move it inside. Okay, what does this buy us? Is that now what we have inside, let's call it something, let's call it zi of h. These are independent random variables, agreed? The data is independent, so they're independent. They are identically distributed, also clear, because xi, yi's are all identically distributed. There are mean zero. That was achieved by subtracting the expectation. Random variables. So what we see there is nothing, it's not a bad thing. It's a sum of independent and identically distributed random variables. Mean zero. Ah, that's cool. We know a lot about them. So let's write this 2 supremum 1 over n zi of h. Sum of independent and identically distributed random variables. Good. They're different for each h, and that's why I put at h. And that thing is called the empirical process. It's a stochastic process, meaning that it is a collection of random variables that depends on some parameter on h. Usually, like in Brownian motion, h denotes time. But in this case, h doesn't denote time. H is whatever, the function from the hypothesis class. So it's not time. Still, it is a stochastic process, and we would like to bound the maximum of the stochastic process. This specific process is called empirical process. It's a big area of probability theory that studies those kind of processes, empirical processes. Good. Okay, so we should feel good now. It's really a sum of independent and identically distributed random variables, and we have a ton of tools to bound it for each h. Chernoff and Hoeffding and Bernstein, whatnot. And then let's do it. Let's do it. Let's actually narrow a little bit down the problem. Let's look for binary classification from now on. It could be generalized, but it's just a pain. Binary classification where the labels and the oracle output either 0 or 1. So for binary classification, the loss function is also either 0 or 1. 0 if the labels match, and it's 1 if the labels mismatch. So in this case, this is 0 or 1, and we subtract expected value. So zi of h also will be between 0 and maybe -1, but yeah, it will be either -1 or 0 or 1, right? So either case is bounded by 1. Good. Okay, so we have a sum of independent, identically distributed, mean zero, random variables bounded by 1. Great. What else can we hope for to bound this? Nothing else. Let's do it. So how do we do this? We apply some concentration inequality. Maybe Chernoff or maybe Bernstein. Let's see what we need. Zi of h. I'm setting up the stage for a concentration inequality. It says something like this, that the sum is greater than t. The probability of that deviation is small. Right? Its mean is 0, so it doesn't deviate from its 0 mean too much. So that's the probability of that is bounded by something. Now, nobody really, you probably don't remember all these concentration inequalities by now, right? We have to look up. But let me give you a little hint of how, I also don't remember, how you can, like a rule of thumb, how you can reconstruct these inequalities. To reconstruct the concentration inequality without remembering it, you normalize things as if it was random, as in the central limit theorem. So instead of dividing by n, you need to divide by root n, by the standard deviation. So this would be, that normalization is like in the central limit theorem. I need to correct this. This is t root n then. And then if the central limit theorem holds, then that would be the normal random variable, right? This will converge to the standard normal. And if it doesn't, concentration inequalities that we studied, in particular, in this case, it was Höfding's inequality. So apply Höfding's inequality from lecture 7. If we apply it, it will give us the Gaussian tail. It will give us a Gaussian tail, and specifically the Gaussian tail is this. E to the minus t square over 2. But our t is really t root n. Yeah. Good. Agreed? Okay, cool. So this is why is it so good? It's good because the thing becomes exponential in n. N is great, n is big. So exponential in minus n will drive this probability down to 0 very quickly. So we did this exercise for one specific h. For each h, we get this bound. Now we need to take the union bound over all h. That's what the supremum is doing here. We need to bound this uniformly at the same time, simultaneously for all h. So that's our next step. Union bound. Again, the probability of a bad event. Let me put it down. The bad event is that the sum is greater than t. Okay, how do we handle this supremum? Supremum is larger than, or maximum, let's say, just for maximum is larger than t. What does it mean? It means that there exists h for which blah, 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 this is larger than t. Exists means the union. We're looking at the union of sets, right? Union of events over all t. And probability of the union is smaller than the sum of probabilities. So I'm putting the sum here, like this. Probability 1 over n. Zi of h is greater than t. Is this step clear with the union? Yeah. Okay. Good. Yeah, perfect. So, well, that's fantastic because how many? This is a sum over this many terms, and each term will already bounded by e to the minus t squared n over 2. Aha. Let's bring h into the exponent. Minus t squared n over 2. That's so nice. So let's say I would like to have it less than 0.01, for example, any number could do. We would like to, this is a bad event. I would like to have this probability very, very small. For that, that will happen if we choose what t. T should beat the log. T should kill this logarithm, basically, should overpower the logarithm. So t should be a big constant times root log h over n, I think. Yeah, and think of c is sufficiently large. Then when we square the t, multiply by n over 2, we get log h, and it will kill that log h, and it, yeah, that should work, right? Good. Great. So what we proved a useful, our first useful generalization bound. Generalization bound. It says that if the hypothesis class is finite, then, okay, let me look up, then what? Then we're applying this thing, applying this generalization lemma, and that term gets bounded by what? By t. I think. Yeah, by t, which is this. Okay, then the test error is smaller than the best possible you can do ever. And that is the cost. This is the most important term. This is the cost of generalization. This happens with high probability. With probability, we get 0.01 as a bad event, so the good probability is a complement, 0.99. So what is this is saying? Let's say I would like this to be bounded by 0.01 also. Okay, we want this to be a very, very small cost, small risk of generalization. And that happens if n is greater than another c, let's say big constant c, log h. So the main message of this generalization bound is that the ERM algorithm, meta algorithm, generalizes well. As opposed to memorizing the data, it actually generalizes to new data. From the training data. And how many training data do we need? About log h. From this many training data points. This is a practical message on how large should be the data, the training data, to build an algorithm that not just memorizes the overfits, but actually generalizes. This is how much. Just take the log of the number of hypotheses. Questions? Ask me questions, guys. You're so quiet today. Okay, criticize this algorithm. I know that I'm giving you like a meta algorithm to say, okay, machine learning can be done in general from this. And why do we need the machine learning? Just what's bad about this? Okay, what's good? Okay, first of all, let me tell you what's good. The good thing is that there's logarithm, right? So the class can be very, very large. You can have a lot of hypotheses here, and the logarithm is a function that grows very slowly, and so you don't need a lot of data. So logarithm is good. We like logarithms. What's bad? You tell me. Or maybe not so good.
Maybe it's only binary classification.
Yeah, well, first of all, it's for binary classification. That's right. If we go back to where we actually needed binary classification, it was to bound the loss function, which bounds our random variables, which allows us to apply Königs inequality. Okay. Now, if we didn't have binary classification, then the loss function will not be exactly bounded, but it could be like sub-Gaussian. It still could apply other inequalities, like Bernstein or other versions of inequality. So that is a good comment that binary classification was a little bit restrictive. However, it wasn't critical. This could be generalized to real classification, to real problems, real value problems. There's another big thing, like an elephant in the room here. Why have we even assumed that the hypothesis class is finite? So remember, what's a hypothesis class? Let me do this here. So we choose a hypothesis class of functions and so on and so forth. Why is it even finite? We usually include for linear regression. What's a hypothesis class for linear regression? It's all linear functions. And we choose the best linear fit. So we choose the best linear function that fits the data. And how many linear functions we have? Infinity, continuum. We can't really assume that it's finite. And similarly for others. It's only for the hypothesis testing where we have this hypothesis or this hypothesis. We have to decide between the two. Then we have, of course, hypothesis class that's finite, but generally not. In machine learning, we have infinite hypothesis classes. So this theorem is good. It's an indication that even for large hypothesis classes, algorithms generalize well, but it is, I would not say bad. Its deficiency is that it assumes that the class is finite, and really it is not finite. In machine learning, we have infinite classes. So the big question now is to how do we handle infinite hypothesis classes? For example, the class of all linear functions. Is there some measure of complexity, instead of taking the cardinality, which would be infinite, is there some other measure, a measure of complexity of this class, the intrinsic measure of complexity that controls the generalization bound? In other words, instead of log, can we put something else there that would be a measure of complexity of H, and for which the generalization bound will still be true? Something like a volume or area or something like that. Something that's finite for infinite sets sometimes. Lebesgue measure, something like that. Is the question natural? Yeah, clear? So we need to handle infinite classes, and we need some other thing there instead of log H. Okay, here's where a mathematical theory starts to kick in, and this is a very beautiful mathematical theory that we will cover now, and what can be put in instead of this, instead of log H, is called the VC dimension. VC dimension. This is named after Vapnik and Chervonenkis. Vapnik, I don't know. And Chervonenkis, who developed this theory in the, I think, in the 70s. Okay, it's a little, it's not a difficult definition, but it is something that you have to spend a lot of time understanding, and that is what the homework will be about. Heuristically, what it should be a measure, the VC dimension, this thing that replaces here, it should be something that controls overfitting. The more data our hypothesis class can overfit, the worse it should be. The larger should the quantity be. The smaller overfit, the smaller quantity. That's something that overfits. So VC dimension, heuristically, it's the largest number, it's a maximum number of points H can overfit or memorize, exactly. It's kind of a memory capacity of H. And here is a formal definition of what that really means. Now we can forget the learning theory completely. It's totally mathematics. Nothing is, it's a beautiful theory, even if you remove the applied component. And it applies for any, let's do binary classification, any collection or class of Boolean functions on any set X. So Boolean functions means that this is a function from X to 0, 1. So we say that H overfits, or the term that's already accepted is shatters. That H shatters or overfits a subset of data, let's say these points, x1 through xd, if it can memorize, if it can realize any label assignments on these points. So whatever label assignments I give, there is a function in the class that exactly realizes those assignments. So this is exactly what we mean that H overfits this data, right? I give you the points. So there are some points that for whatever label assignment, there is a function that memorizes, that realizes them. And the VC dimension of H denoted, which we'll denote by simply VC, like this, is the maximum cardinality, maximum D. D of a subset that H shatters. The largest number of points on which any possible assignment is realizable. Let's take a minute to think about this. How does that sound? Good? Definition clear? We'll go over like, how many examples I have? I have 8 examples here, just to make sure that you understand this definition. First example. Just take one function. And that by this one, I simply mean the function that takes value 1 for any x, just a constant function. Take a constant function. What's the VC dimension of the constant function? VC dimension of the class of one function. It can't even memorize one point, right? If I give you any point, if I give the class any point, it's constant. It's just fixed value there. It can't realize any possible assignment. To shatter even one point, there need to be two functions in the class. One where the value is 1 on that point, and the other where the value is 0. And it doesn't have that. So VC dimension is 0. It can't shatter even one point x1, because the value on x1 is 1 always, and it needs to be 1 or 0. Have to be two functions. Second example, less trivial. Half lines. H is the set of all indicators of the half line. That means that by this one, I just mean the function that's 1 on the set from -infinity to a. And 0 elsewhere. So it's this function. And as we vary a, we have different functions here. Infinite class. Okay, so we claim here that the VC dimension is 1 for this set. Let's see. VC dimension is 1. What do we have to demonstrate to prove that the VC dimension equals 1? Two things: that H can shatter some one-point set, x1, but it can't shatter any two-point set, x1, x2. Okay, that was literally the definition of VC dimension. If it can shatter some one-point set, but can't shatter any two-point set, the VC dimension is 1. VC dimension is the maximum size of the set. Good. Let's see. So how can it shatter one-point set? Let's take actually any x1 is good. Any x1 is good. And let's say this one. I need to find, to check that H shatters this point, we need to find two functions. One that takes value 1 on x1, and second that takes value 0 on x1. This way it will realize any assignment. Well, that's easy. This is one function. This is another function. Takes value 1 here, takes value 0 here. So H of x1 is 1, H of x1 is 0. Another function. Good. There are two functions, so any possible assignment, label assignment, can be realized. But it can shatter a two-point set. Why? So easy. Can shatter. So for this, I need to find a bad label assignment. A bad label assignment. What would be the bad label assignment here? 1, 0 can be realized like this. 0, 0 can be realized. 1, 1 can be realized. 1, 1 can be also realized. No, one can realize this differently this way. The only assignment that cannot be realized is, I believe, 0, 1. Because no matter how all functions are like this. So no matter how I place this function, this way, not good. 1 is not realized. This way, not good. 0 is not realized. This way, neither is realized, right? So 0, 1 can never be realized, whatever I place this function. So this assignment can't be realized. And that's why H can shatter at any 2-point set. And we proved that VC dimension of half lines is 1. Good. Yeah, is this clear? Yeah, it will take you a little while to get used to this definition. Best way to do this is to do the homework, or go over these examples again. So intervals. Here the class consists of indicators of two-sided intervals, A, B, for any A and B. So a function in this class looks like this. And this is 1. And we vary A and B. A and B can be different, and this gives us different functions. Okay, so we claim that VC dimension of H is 2. Let's prove it. So we have to show that H can shatter some 2-point set but cannot shatter a 3-point set. Any 3-point set. Okay, shatter some 2-point set. Doesn't matter which one. Let's say x1 and x2. And let's try to prove it. There are 4 possible assignments that H must realize. 0, 0. 0, 1, 1, 0, and 1, 1. Okay, again, we claim that H shatters this set, and therefore it must realize any of these 4 possible assignments. But that's easy, right? How do we find functions that do this? 0, 0, for example, that thing. It's a function in our class. It realizes this assignment, 0, 0. 0, 1. Oh. 0, 1. This function realizes it. 1, 0. This function realizes it. 1, 1. This function realizes it. All of these functions are in our class. And so H does shatter this 2-point set. Yeah, good. Cool. Okay. But can shatter any 3-point set. Okay, now I need your help, guys. Let's say I take a 3-point set, any of it. What's the label assignment?
1, 0, 1.
1, 0, 1, exactly. Yeah. I think that's the only one, right? Because no, yeah, that's the only one that it can't realize. 1, 0, 1. Because to be able to realize that assignment, I need a function something like that. Like a double. Oh, I need a function something like this. And that function is not in our class. So this assignment is not realizable by the class. Okay, getting better now? Yeah, you feel good about this definition? Everything is good? Good. Let's go over examples. We have still 4 examples left. Half planes. Now we go a little bit higher than dimension 1. Half planes in R2. H is what is the, well, basically it's this. You half planes is this. Easier to put it on the picture than to write the definition of it. It's a function that takes value 1 on one half plane and 0 on the other half plane. And then the interface is any line. So H is the indicator of a half line. I guess A1 x of 1 plus A2 x of 2, second coordinate of x, maybe plus b is greater than 0, as A1, B1, A1, A2, and B1 vary. B vary. What's your guess? You see dimension? All right, we'll prove it's 3. 3. So for this, we need to show again to check 2 things, that H can shatter some 3-point set, but can shatter 4-point set. Okay, let's do the 3-point set. This, for example. Let's just think, instead of there's what is it, 2 to the 3, there's 8 possible label assignments that we should check, but let's just fix one, 0, 0, 1, 1. How can I realize that? I will put the line here, and the half plane will be here, and the function takes value 1 here, value 0 here, and it's realized, right? So I realized this label assignment very easily. And similarly, we can do any other assignment, for example, 1, 1, 0, 0. Again, put the plane here. And half plane is, and half plane is there. That's it. So any 8 assignments are realizable. Just one more. Maybe 0, 0, 0. Easy. 0, 0, 0 is easy, I think. Just put plane somewhere else, very far. And that's it. Okay. The lecture notes have a more technical, like I put all of the 8 of them, but is it clear? Yeah, intuitively, that's all possible assignments are realizable. Very good. But can't realize, but can shatter 4-point sets. Shatter any 4-point set. Okay, there are different configurations of that 4-point sets can take, but basically they're all isomorphic to the following 2. 4 points on a plane can be either in a convex position, like this, or in a non-convex position, like this. Convex position is like the convex hull is a quadrangle, and non-convex it's a triangle. So we have to show that we have to find a bad label assignment for each of these positions. So the bad label assignment here, it should be non-linearly separable, right? So it should be something like maybe 0, 0, 1, 1. I can't separate zeros from ones by a line. That should be clear. No matter how I put the line, this way, no matter how I put the line can't separate zeros from ones. And in this position, it's actually easy. It's this. Right? I can't separate one from the zeros by a line. Again, no matter how I put the line, there's I can't have one on one side and zeros on the other. Good. Any questions?
I have one question. Why, where we see 3 points, we don't look 3 points on the line?
Ah, that's true. Yeah. Actually, 4 points here. So to prove that H has VC dimension 3, we have to find some 3-point set that is shattered. So we have to just find one example, and that's it. But we have to show that no 4-point configuration can be shattered. And here we have to also, there are other configurations that we have to check. For example, this. Oh, this is convex, sorry. 3 on the line, so 3 on the same line, maybe like this. Yeah, you're right. There are other configurations that points that we should check, and either way, those are even more difficult to realize. I think this would be a non-realizable assignment. Yeah, 3 points on the line and another outside, and then all 4 points in a line. That's even easier. 0, 1, 0, 1, for example. That's not not linearly separable. Yeah, good. Any questions again? Good. Hey guys, because on Friday we don't have a class, if I take 5 minutes more of your time, is that okay? Because I just want to finish with a couple examples here. Okay. So more realistic examples is we have the same situation, but in higher dimension. Half spaces in RD. So before we looked at the plane R2, now we're looking at RD, and the class is indicator functions of the half planes, and the half planes are like this. Wx, that's a linear function, plus b, that's an offset, is greater than 0, where w is an RD and b is an R. I put it this way because in RD, the equation of a hyperplane, the plane of dimension d-1 is this. This is all x's for which wx plus b equals 0. And then we just have one side of it like this. And put 1 there. 0 there. So that's a half planes. This example is important because that's exactly the class of linear classifiers. For example, in support vector, we looked at them in support vector machines. And we would like to separate the cancerous patients from non-cancerous patients. Remember that? Linearly separate. So this is a very interesting, very useful hypothesis class of linear classifiers. VC dimension of H. Well, let's see. In dimension 2, the VC dimension is 3. In dimension D, the VC dimension is D plus 1. prove that. I have more examples in lecture notes about polynomial surfaces of degree r, then the dimension is something like this: d plus r, choose r. So for polynomial classifiers, there's also, so if this is a polynomial surface given by polynomial of degree r, then this is a VC dimension. If example 6, if h is a function, if you look at all functions that a network, a neural network, can compute, with, let's say, with activation function like this, with 0 or 1 activation. So simply, if you forget what neural networks are, it's simply a superposition, a composition of linear classifiers. Visually, it looks like this. There is a lot of connections here, maybe this, and X comes as an input to the neural network, and Y comes in as an output, but each layer computes a linear classifier of this form and puts it into the next layer and so on. The VC dimension of H is bounded above always by something like the number of connections, almost, W log W, where W is the number of connections or weights. As you vary the weights of each connection, basically you're varying W here and B in each time. Neural network can compute different functions, and how many of what's the VC dimension of that class? Well, it's proportional to the number of these connections. At this point, heuristically, so this is where things will become hand wavy. In all the examples above, the VC dimension H is about the same or exactly the same as the number of parameters. That are needed to describe a function in H. I don't know if you noticed that. This is let's go back actually. Example 1, just one single function. We don't need any parameters to describe it. It's always the same function. VC dimension is 0, no parameters. Example 2, half lines. We have just one parametric family, one parameter, VC dimension is 1. Intervals, we have 2 parameters, A and B, to describe the class. VC dimension is 2. Half planes, we have 3 parameters, A1, A2, and B. VC dimension is 3. Half planes, half spaces in RD, same thing. We have D parameters in W and one more parameter as an offset, B. Then things become a little iffy. In neural networks is also, W is the number of parameters, number of connections here, but up to log factor. So it's generally true, I guess, as a first approximation to the truth, that VC dimension should be proportional to the number of parameters that needed to describe H. Although, I don't know, it's a minefield. Sometimes it's very not true. For example, if the neural network, instead of this activation function, has a sigmoid function, then I think the VC dimension is actually infinite. I can't remember. And if it has ReLU activation, the VC dimension is W times the number of layers times log W, something like that. So This heuristics is a very, this heuristics is a very good first step to approximate the truth, but it's not always true. Okay, good. I'm done now. Any questions? Sorry for going over time. No questions, really? This is fun stuff. Okay, let me stop recording. If everything is good, then we will meet with you not this Friday because of the Thanksgiving, but on Monday.